constant acceleration equations. Now, the thing to remember is these equations are only valid when something is undergoing a change in acceleration that's constant. Now, luckily, things falling under gravity, acceleration is always constant, so they work in that situation. Well, let's have a look at this very simple velocity time graph. If we want to try and work out what is the change in displacement between these two times, between, say, time 1 and time 2. So we're talking about delta t, that means the change in time. How far have we travelled? Well, if we think about our velocity formula, it's delta r over delta t, and therefore delta r is going to be v delta t. Now, have a look at that. Delta t is the base, and v is the height of this rectangle, and so really the change in displacement is simply the area underneath that rectangle. Okay, but what would happen if instead of being a constant velocity, it was a constant acceleration? So we've got an object that's accelerating at a uniform rate, and you can see this graph, the gradient being a straight line there, the gradient's constant. That tells us that it's accelerating at a constant amount. So how would we work out what the change in displacement in this situation would be? Well, first of all, it's going to be the area under the red area, the area under the rectangle, and we already know what that is. But of course it's accelerating. What we need to do is, let's just put that down there. So this is our initial velocity when t1 starts. That's the velocity is when t1 starts. And this is our final velocity, so that's going to be v, which makes this area here, the height difference between these, v minus u. Okay, just as a bit of an aside, remember the acceleration formula is v minus u on delta t, and therefore v minus u equals a delta t. In other words, this height here is also a delta t. We'll bear that in mind for the moment. Okay, so we're working out the area under the red one. Well, it's simply going to be the height here. It's going to be u times the change in time. But we have to add on, so it's going to be a plus. We have to add on this green area here, the area under the triangle. Now, the formula for the area under a triangle is a half base times the height, if you remember. So that's going to be a half of the base, or the base is delta t, times the height. Now, what's the height? The height is a delta t. We can simplify that down to is that delta r equals u delta t plus a half at squared. Okay, and just by convention we tend to drop off the delta t's and we write it as ut plus a half at squared, but never forget it's always delta t, it's always the change in velocity. And that is our green boxer. But before we finish, let's just have a look at that formula. What it tells us is the distance something travels when it's accelerating at a constant rate is proportional to the square of the time. Remember, Galileo found that back down in his original analysis, rolling things down an inclined plane. So there you go, physics is internally consistent. The other thing to remember is, if we're talking about projectile motions, of course, acceleration is only vertical. And because we can consider the vertical component of motion completely separate from the horizontal component of motion, what we're going to do is we're going to call that the y dimension. Is going to be equal to uyt plus a half. Remember, acceleration is g on Earth, or it could be a different acceleration on a different planet, a half gt squared. And that is the form of the formula that we're going to use for projectile motion.